Hello there, folks. Can everybody see and hear me? Please raise your hand if so. All right, great. I'm going to wait just a minute before I get started. Just as a reminder, I would like for everybody to be connected with Edmodo. If you missed last class for whatever reason, um, these are the Edmodo codes for your corresponding class. And just want to make sure everybody got that. I'm also including the links to our Facebook page as well as our YouTube channel. Just as a reminder, if you miss a class, we will be putting all of our classes up on YouTube. So, question. Should you still be connected to Charlotte? If you have lab in Charlotte on Thursdays, you should be connected to this code right here. If you do labs in Charlotte on Saturdays, you should be connected to this one right here. Oh, not from last semester. These are new codes. Yeah. So last semester's codes won't work for this. I think that those should be in legacy mode, meaning that they're no longer active last semester's codes. So I'm going to put your hands down. Like I said, wait just a second before I get started. Any questions on anything that we did last class, including, connecting to Edmodo or anything about engineering in general, why it's cool, anything of the sort? Another question here. Looks like Samuel's all good. All right. Awesome possum. So today we are going to get started on Perch. Okay, so Perch is some pretty cool stuff here. We'll be building robots in your lab sessions. And just out of curiosity, does anybody in the distance lab, can you tell me if we did have lab on Saturday, or did it get snowed out? Or iced out, rather. Anybody that does Saturday labs in Raleigh, or sorry, in Charlotte? It got snowed out? Okay. We'll be in contact with you when the makeup lab will be. Probably for the better that we didn't have lab if it was anything like it was up here in Raleigh. Pretty gnarly. As a reminder, Raleigh does have lab this Saturday at 11:30 a.m. So I look forward to seeing those of you from Raleigh here at the Science House. We'll get in contact with you. And without further ado, we will go ahead and get started talking about the Perch. Those of you that did have lab already probably already got started building the frame of the Perch. So this will be a little bit reviewy for you, but it's okay. We'll talk about some new stuff as the class goes on today. So, what is Perch? Perch is actually a program where you get to design and build your very own underwater robot. We are using Perch as an opportunity for you to learn new engineering concepts, develop problem-solving techniques, to work in a team, to gain knowledge of the engineering process, and as everything we do, our main goal is for you to have fun. We want to get you excited about engineering for your future. So I'm going to show you a quick video about Perch. And actually, before I do that, I see somebody missed the Edmodo codes when you logged onto Edmodo. I'll put the Edmodo codes right back up just real quick. So I'm assuming, Cameron, you'll be Charlotte Thursday. Good to go, or here's another question I see. You're Charlotte. Oh, you're Charlotte Saturday? Oh, okay. Well, my bad. There's your code. I hope it works. It should work. Okay. Okay, cool. The question is, can you put the Sea Perch link in the chat? I was going to show it to you, but I'll also put it in the chat just so if for some reason video issues are happening for you, then you can watch it on your own time. But I will be showing it right now as well. So, we all good on the Edmodo codes? Anybody else need it? All right. So I'm going to go ahead and show you this. Let me know if you can hear it and everything. If you can't, I'll just give you a minute to listen to it on your own. But here goes. Y'all hear? It's really quiet.
This week, Lab TV travels to John F. Kennedy High School in Silver Spring, Maryland, where Navy engineers are helping kids build some very cool
Here, the audio's cutting out. Okay, and I'm honestly not surprised that audio's cutting out. That does happen. You haven't really missed anything if you're just now getting on. I'm just introducing you to Sea Perch, which is what we'll be doing in lab. Because if your audio is cutting out, I did send you the link in the chat to the video. If you're having some issues with it. I'm seeing some people have issues, some don't. You could hear it. Alright, well, this is the link if you're having audio issues with that. I'm going to go ahead and keep watching it here. I will be going over most of what's going on in this video as the class goes on today, so don't be too upset if you can't hear it well.
underwater vehicles. It's called Sea Perch. Kids learn about engineering, science, and math while they create their own water robots.
It's a Sea Perch. It's called a ROV, a remotely operated vehicle.
Something that scientists will use. It goes underwater.
So it's like what they used to find the Titanic.
Of course, these are not the same underwater robots that the Navy uses, but they operate on the same principles. It starts with building the Sea Perch frame. The kids use PVC pipe.
They gave us long ones and we cut them, but we had to construct the actual structure.
On the first day, we pretty much cut the PVC and put the floaters on, and the second day we started the motors, and third day I put the propellers on. And then today we built the circuit board boxes and we labeled them for if the motors go forward or backward.
To power their Sea Perches, the kids use a battery connected to 3 electric motors. These were potted in wax to make them waterproof. They also wired their own electrical circuits.
It overwhelmed us in the beginning, but when we got all the steps, put it together and it's pretty easy.
In this electrical circuit, a battery supplies the power. The energy that leaves the battery must return. That's why it has 2 terminals, negative and positive. Negatively charged electrons travel through wires to power a load, like the motors, and then return to the positive terminal. When you flip a toggle switch, the circuit is closed and the motors spin. When it is open, the motors stop.
We had to solder everything on the back.
Here you can see all the soldering things we had to do.
One of them is for making it go down, and one of them is for propelling it up. It was really fun putting it together. I just can't wait to see it go in the water, and we just hope it works.
Yeah, that's the biggest goal, make it work.
The kids take their vehicles to the Carderock Naval Lab to try them out. But first, the Sea Perches need to be made neutrally buoyant.
Right, if something is buoyant, that means that it floats. So today you're going to get your Sea Perch to be what's called neutrally buoyant. It's not quite completely floating, not quite completely sinking.
Buoyancy is the upward force that keeps things floating. It is determined by the weight of an object and the weight of the water that the object displaces.
I'm going to put the weight in a cup of water. It displaced water into my box. So here is how we find out if something is going to float or sink. If I weigh my weight and I weigh the water that it displaced, if the weight of the weight is heavier than the weight of the water, it will sink. If the weight of the object is lighter than the water, it will float.
And now for the fun part, some awesome underwater action.
It makes me want to get into engineering when I go to high school, because usually at first I wasn't that interested, and then I found out that we could do stuff like this, so now I'm interested.
And it looks like we have a whole class of future engineers. To find out more about sea perch,
Alright, so that was probably a lot to take in, since you don't know very much about what's going on yet. I will go further into the electric circuits, the buoyancy and everything, and in lab we will be testing it in water, but not necessarily at that fancy naval base. We're probably just going to be using kiddie pools, which do work, but we'll get there when we get there. Alright, so that's basically what we're going to be working on in our labs for the first little bit of our semester. Alright. So, as you saw in the video, the Sea Perch is a simple ROV, ROV standing for Remotely Operated Vehicle, made from PVC pipe, motors, and floats. You're going to be using the engineering design process to create and test an ROV that will maneuver underwater. And I see kiddie pools are good for sledding. That is interesting, I did not know that. And speaking of sledding, I hope y'all stayed warm over this crazy weekend. It was a little bit hectic outside, I saw, but hopefully y'all got to enjoy the snow or the ice or whatever it was your city got. So, I digress. Anyways, you're going to be learning a whole ton of stuff, specifically ship and submarine design. The whole goal is to design a submarine, so I very much hope that you learn that. You'll be learning about buoyancy and water displacement. If you remember from the video, basically the weight of the object in water versus the weight of the displaced water is what causes buoyancy, and I'll go more into that probably next class. Propulsion, since we will be using motors to propel our Sea Perch. We're going to be doing some more soldering, and if you've done class with us before, you already know how to do that. But we will be using other tools as well, and learning about tool safety. I'm all about some tool safety. You'll be learning about vectors, which is basically a line with a magnitude. So you'll learn about that, don't worry. Electricity, circuits and switches, as you saw in that video. Learn how circuits work and what switches do in electric circuits. Ergonomics, which is just a fancy word to say working with people efficiently. Waterproofing. It might surprise you, but electric circuits don't really like water, especially the motors. You'll need to learn how to waterproof. Depth measurement, so hopefully we'll have an instrument on your Sea Perch that will measure how deep underwater it is. Biological sampling, I really don't think we're going to be doing much of that, to be honest. Attenuation of light, which is basically how light behaves when it hits water. So if you've ever gone underwater and saw your arm looks like it's detached, that's light attenuation. You'll be learning about moment arm and the basic physics of motion. Yeah, Caleb got it, refraction basically. And then we will talk some about career possibilities, just inherent to the teams that you will be working in. Okay? Any questions on that? All the crazy stuff we're going to be doing. All right. Exciting? Yeah, I'm really excited about it this year too. I've read a bunch about sea perch, and apparently it's one of those things that teaches the teachers, and I love learning. Never stop loving learning, no matter how old you get. It's a big part of succeeding in life. Now, which tools will you use? Safety glasses. You folks in Raleigh know how much I love safety glasses. They're not tools, but they're a tool for tools. So a couple questions I see. Do we each build our own robot, or do we work on one in a group? It depends on which class you're in and how big your classes are. I believe that the Raleigh classes will be working in groups of 2. Other locations might have groups of 3, but I think that at least you're going to have a group of 2. At the bare minimum, you won't be working alone. The question, which career will Sea Perch be in? That's actually a really good question, because there's different parts of the robot that have to be put into consideration. The careers span from structural engineering to electrical engineering to mechanical engineering, as well as quality engineering specifically. And you'll actually have your own roles assigned to you during the lab sessions. So if you really don't like electronics, you don't necessarily have to do them. So how will we work out who gets to keep the robot? Old school fist fighting. No, I'm just kidding. You and your partner will have to talk about that. It's one of those things where you have to work in a team, and I am sorry that you can't each keep it, but that's what cameras are good for. So you can show your friends. That's why we do encourage you to work on your digital portfolio and FaceTime with Sea Perch. You each are making one in Charlotte? Well, I actually didn't hear about that. Maybe we will be doing our own. I just thought that we'd be working in teams. Let me clarify that, and I'll get back to you Wednesday, but it looks like Charlotte's doing their own, so cool. With blackjack, I mean, hey, if it works, it works. So maybe we will get all your own, so cool. And that actually would be awesome, so that you can show your friends. Anyway, so safety goggles are a must with some of these tools, not all of them, but a majority. A saw is one of those tools that is very important that you wear your goggles for. You don't want any flying piece of PVC coming at you. You don't necessarily need safety goggles for a screwdriver, but you will learn to use that. I hope you already know how to, but you'll be using a drill and drill bits. We will be drilling holes into our PVC pipe. You'll be using a vise or a clamp to keep something steady when you're working on it. Pliers, I don't have much to say about that. A ruler, scissors, y'all probably already used those in your life before, I hope. A hot plate to melt the wax, and soldering irons to work with our electronics. Good question, will we provide all the equipment, or should we bring things? We will be providing all the equipment. I know for a fact that we're not going to be giving out the battery for the Sea Perch. That's something that you'll have to do on your own. I will have batteries for it in lab. We're just trying to keep costs down. So we'll have everything, but when you get to take it home, you might have to supplement certain parts with your own parts. But you'll get everything else. And we'll give that to you. What kind of battery does it need? I think it's a 12-volt battery. But let me get back to you on that as well. Yeah, good questions, y'all. Cool. So I guess this is incorrect. I guess we're working in teams of 1. So I guess by yourself. Your ROV is expected to be remotely controlled. Kind of misleading there, and I'll explain why in a minute. It will be connected to a tether. The tether will be how you control. It's how you control your robot remotely. Samuel's saying that you keep the motors. Okay. So that means basically you're keeping everything except the battery at this point. Battery and controller. It will be connected to a tether. It will work when it's submerged in water, hence the waterproofing. It will be able to move left and right and rise and fall to and from the surface. Okay, so that's the buoyancy that we were talking about earlier. Specifically, what you will be receiving is all of this stuff. So 5 to 8 feet of half-inch PVC pipe, PVC connectors, 3 motors with propellers, holders, and containers, 2 floats, tether wire, so netting for your robot, which will have some twist ties so you can put the netting on it. You'll get some screws. Yep, there we go, one 12-volt battery. You'll get a circuit board and a control box. You'll get a Cat5 wire. I believe those are just like your Ethernet cords. You'll get a wire. Wow, that's big. You'll get some solder and soldering irons and stuff. You'll get electrical tape and some rubber tape, as well as the tools that we will use to create it. Now the question is, can it go forward? Yes. The way that you're going to be mounting your motors, well, it depends on how you individually want to do it, but it can go forward by putting your 2 turning motors on at the same time, basically. So to turn right, your left motor would be the only one on. To turn left, your right motor would be the only one on. To go straight, they're both on. To go backwards even, they're both on, just the other way. And in lab we'll have diagrams and stuff for you, so to make it sound a little bit easier, since my explanation's a little bit vague. And included in the official kits, this is what you'd be getting. This is also ideally what we'll be giving you. Hooray, cool stuff here. It won't look as nice when we give it to you, probably. Not all organized. So the design requirements, other than what I've already told you about the challenge, is that the frame is going to be made of this half-inch PVC pipe. The frame will hold the motors, the floats, and any weights that you may need. You might need weights, say, if you cannot neutrally make your robot neutrally balanced. You might not need it. It really depends on your design. The motors are going to be positioned on the frame. You can't just have floating motors. That'd be kind of weird. The motors are expected to submerge the ROV, move it left and right, and raise it to the surface. And the ROV must be powered by a 12-volt battery and tethered to the control box. So even it's not remote controlled, it's remotely controlled. So that's how you're going to maneuver the ROV. So the question is, when is the Charlotte lab rescheduled for? I'm not entirely sure yet, to be honest. Mr. D will be in contact, or actually Mrs. D probably will be in contact with your parents about that. If you do have like a scheduling conflict or anything, definitely email Mrs. Dubik sooner rather than later so we can try to accommodate everybody. Because we want everybody to have, equal lab time so that they don't have to catch up or fall behind or anything, So these are your design requirements, the very, very baseline. Obviously, you'll learn more stuff as you go on that you have to take into consideration. So now that I have gone over everything that you're going to be doing, let's talk about engineering design so that we have an idea of how to get started on our robots. So the first part of engineering design is describing your challenge. What are you building? Anybody tell me? What are we building? A robot. A robot that does what? An underwater robot. And I wish that our robot would love. That would be a very interesting design thing, but yes, we will be doing ultimately a Perch, which is an underwater robot. It is stuff. We are building a robot in stuff. So there we go. And how do you want your robot to be used? This is the sub part of your first question. How are you going to use this guy? To do stuff, yes, very plainly, but what kind of stuff? Yes, fun stuff, cool stuff. Move, definitely, that's a good one. How are we going to make it move? Oops. To help grab things underwater? Yeah, definitely. Basically, we're going to be building this robot to go underwater, to swim around, maybe take pictures. I'm not sure if we're going to be getting cameras or not, but I would love to have that. Record maybe information, yeah. And as a result, what capabilities should our design have? It should be able to swim around. It should be able to do some cool stuff. Y'all are right in that regard. So that is your challenge, to build a robot that has these certain capabilities. So, what do we already know about ROVs, other than what we've already seen, or including what we've already seen? Not very much, right? We've seen, a couple second long video. We've seen a couple pictures of it. We do know some things about ROVs. Not Mars, necessarily. I mean, I guess Mars rovers, which is actually interesting because I did my senior design project on Martian rovers. Those are remote controlled, not remote controlled and remotely controlled. This robot is just remotely controlled. But to figure out what we know about ROVs, we gotta do some research, right? But y'all are lucky. I've already done some really basic research on ROVs for you. ROVs generally are linked to the ship by a tether, which consists of just a bunch of cables that carry, say, electrical power, video, maybe data signals, back and forth between the robot and the operator. What always breaks, ROVs or Mars rovers? ROVs? I mean, I guess not always they break. Well, hopefully yours won't be breaking. That's my goal. Most ROVs are equipped with a video camera and lights, obviously so you can see whatever you're recording. Additional equipment, yours always break. Well, hopefully this one won't. This is a little bit simpler than the ones you've probably been making on your own. Additional equipment that ROVs may contain or include are magnetometers, so just to check the magnetic field of the area. A still camera, so not necessarily a video camera. A manipulator or a cutting arm, so that you can, if you see maybe a cool piece of coral, you can cut it and bring it to the surface. Water samplers, just to see how the water, stuff about the water like salinity. We won't necessarily be doing that for our ROVs. And also they'll have instruments that measure water clarity, so how clear it is, how much light can penetrate the depths, and information on taking temperature of the water. The question is, lasers? Yeah, I can see there being lasers, maybe to test depth penetration. An ROV stands for Remotely Operated Vehicle. We will not have flamethrowers on any ROVs because you're underwater. The question is, will we be building this at the labs and at home? It'll mostly be at the labs. You're always welcome to, once we're done, improve your ROV at home, since you will be taking these home with you. Any questions on what I talked about with ROVs? How it's connected with a tether, has instrumentation, yada yada yada. Just not flamethrowers. No questions? Torpedoes? Generally we wouldn't put torpedoes on an ROV. ROVs are used more for scientific gains, rather than battle. Submarines are more used for that, for torpedoes and stuff. So no, probably no torpedoes on an ROV. Alright. So, at this point, what I'm going to do... actually, wait, I have a question first. Will we attach a camera to it? We're still trying to figure out if we can find a relatively inexpensive camera to attach to it, but I'm not entirely sure if we will end up doing that or not. Could we actually use these in the sea? Yeah, I don't see why not. You might not want to use it at the beach. You might want to use it a little bit farther out so it doesn't get thrown around by the waves. The waves are probably going to be a little bit stronger than your robot can handle. But yes, you could actually use these in the sea. Now, how well you can see in the sea is a different story. You might need to add some lights to it, maybe some more powerful motors. So at this point, what I'm going to do, I'm notoriously bad about doing this, but I do try to do polls every class to see if I'm going too fast or too slow in what I'm teaching you. Again, I'm not very good at remembering to do this, so I'm going to try to do this every class if I can. But I'm going to do a poll asking you how my pacing is. What you'll do is just vote on it, and once you vote on it, I won't bother you about doing it anymore. There should be something on your screen to vote on it. And eventually, when most of y'all vote, I will close the poll, which looks like most of you have voted. So the results are mostly good, some too slow. I am going to keep up with my current speed for now. But yes, the NN opinion, it means no opinion. The NN just means null. It's just a weird error in the software. So that's what NN opinion means. No opinion. So I'm going to continue, so thanks for letting me know how I'm doing. The last question about brainstorming ideas is, do you have any initial ideas about a design? Now this is more of a rhetorical question, since to officially have ideas, you might want to write them down or whatever. But for example, if you don't know where to start, you could take a look at, say, existing sea perches. So notice that these are a little bit boxy. They are made with PVC pipe, so you're probably going to be tending to have a box type structure here, but you don't necessarily have to. You are allowed to do your own designs, but just keep in mind the limitations of what you've got handed to you. So while a spherical sea perch would be really, really cool, can anybody tell me why a sphere wouldn't be necessarily a good idea, just in terms of the materials given? Why would a sphere be difficult to implement? Exactly, PVC pipes are straight. PVP pipes. PVC pipes are straight. If you can make a sphere with this, I would be very impressed. I'm just saying. But ultimately, it is your design and your decision how you want to make this. So the next section is research. What do typical underwater ROVs look like? And I will send you a link to this YouTube video, and I also will show it. So the question here is, it would keep rotating. Not necessarily, if you position your motors correctly, but it really depends on what happens when you test it. The other thing is, it would be very expensive as well, considering extra materials. PVC is pretty cheap. It wouldn't be terribly more expensive, but you would have to provide your own materials in that case. What we're giving you literally is This stuff right here. Anything more, that's up to you. So I'm going to show you a video real quick. And again, I did send you the link to it if you want to watch it on your own time. About one of the underwater robots that was used to clean up the oil spill in the Gulf of Mexico. So.
The Bay Aquarium Research Institute, better known as MMBARI, is getting involved in the oil spill disaster in the Gulf of Mexico. It is sending an underwater robot to the region. The goal is to help determine exactly how much oil has seeped below the ocean's surface. We get more from Action News reporter Ravi Kapoor live in our Salinas newsroom.
Aaron, this high-tech robotic vehicle created by MMBARI is now in the Gulf of Mexico, and it could prove to be an essential tool to help scientists analyze the true damage of this spill.
We've used our AUVs a lot to understand ocean processes. This is the first time we've tackled an oil spill. Oil spills are not our normal business.
From devastation comes innovation. This $5 million autonomous underwater vehicle, or AUV, was never intended to be used for such a calamity. But with the oil spill in the Gulf billowing into month number 2, all hands are on deck.
All of our oceanographic resources are trying to understand the nature and extent of the submerged oil plume that's being created by this disaster in the Gulf of Mexico.
Steve Etchemendy, the director of marine operations for the Monterey Bay Aquarium Research Institute, says this torpedo-shaped robot took 10 years to develop and is normally used to map the ocean. But it's now in the Gulf, delving into waters nearly a mile deep, analyzing what the oil and chemical dispersants are doing to the ocean.
We have the advantage of being able to launch our AUV outside of the oil spill. And because this AUV actually can go 3 knots for 12 hours, that gives us the capability to stand off.
The AUV uses cutting-edge software to navigate the waters, collecting valuable oceanic samples for scientists. Today it's thought to be a complement to other scientific methods, but if all goes according to plan, this AUV could uncover enough information to improve response on spills in the future, and perhaps even aid in the effort to alleviate the worst oil spill in American history.
We'll know more about what's happening than we could have 10 years ago, and certainly a lot more than we could have known 20 years ago.
MMBARI received a contract from NOAA, the National Oceanic and
So a couple of things to note about that. Cameron is correct. That guy does sound like Mr. Dubik. That was kind of silly. This video actually shows what's called an AUV, which is an autonomous underwater vehicle. It's a little bit different than an ROV in that it is autonomous, which means that it can move and sample and everything by itself. So that's just an example of what a typical underwater vehicle would be. Obviously the ROV would have, which is what we're making, would have a tether to it. But notice that that one is shaped like a torpedo. For what that robot's doing, it is using hydrodynamics to its benefit. Obviously things flow better in air and water that are shaped sort of torpedo-like. But keep in mind that you're not going to be going terribly fast. You're not going to be doing crazy sampling or anything. But that's just an example of how you can get some inspiration for your robots. Obviously there's tons of links on the side here that include both ROVs and AUVs, so you can get some inspiration on how to build your own. All right. So the internet's wonderful, just saying. So the components that you will need to include, which is the next question in the research phase, are motors, floats or weights, wires, and a frame. And we will be dividing this up a little bit later, and I'll show you how and why we're going to do such a thing. The next step is going to be our initial designs. The first step, which is drawing rough sketches of your design. I'm not sure if Mr. D had you do that in lab. For those of you that had lab, can anyone verify if you already got initial design sketched? He didn't have you do that? All right. I'm also not sure if he's having you build the baseline robot or the robot that is officially sanctioned by Perch. Either way, that would be your first step for engineering design. And when you're doing that, you got to remember to include the shape of your robot, where you're putting the motors, where you're putting your floats, and where your wires are going to be placed. So even if you don't do that initially, you might want to consider that as you continue building your design. The next step after you do your initial designing is prototyping, or selecting a design which will be the most successful in accomplishing your goal. If you've created some initial designs, you'll have a couple designs made. You just got to figure out which one has the most space to put stuff that are required in the design. But ultimately, that's just something that you have to weigh the pros and cons of each of your designs. And finally, you get to build and test your prototype. Can anybody tell me what you'd be testing your prototype for? Why would we need to test our design before making a final design? Leaks, that's a good one. And watertight, yeah, definitely. It's not going to work if your motors don't work. To see how well your motor works, definitely. A hole in the PVC, not so much, because we are going to be flooding the robot with water. So motor function, yeah, to make sure it doesn't explode or sink. It's not going to explode, but we do want it to be able to sink, but we also want it to be able to float. Y'all got it. The battery is not going to matter so much. If it's dead, we'll get you a new one. And yeah, exactly, just in case something goes wrong. And if it actually works. Yeah, y'all are spot on that. Spot on, y'all. And that leads us to our next step, refining the design. Address problems encountered in the testing stage. If your robot does everything great but won't turn right, you got to address that. You got to figure out what's going on with your motors. You got to figure out maybe it's not watertight, maybe it's just acting weird, maybe you didn't solder something correctly. There's a ton of reasons that it might not work. You do have to address these problems and incorporate it into your design. You have to incorporate it back into your prototype. So when I say iteration, the prototyping and refining stages are iterative, meaning that you can go back and forth between these stages infinite times until you actually find an appropriate design that could potentially work. So say you've done this, your design is working, you can build your final model, which is very, exactly what it sounds like. So while it sounds like a lot, it's not terribly much that you have to do to get this going. But at this point, the question is how we build the prototype. Your prototype's actually just going to be the same as your final model. You're just going to keep iterating it. So keep testing, rebuilding, and your final design is going to actually be the final prototype that you built. So do engineers use these steps a lot? This is the engineering method, or the engineering design method rather. Yes. They might not do all of these steps individually. They might have teams, like ideally we would, where somebody's going to do prototyping, someone's going to be doing the research. Engineers don't always do every single one of these steps. But overall, in the design process, they will. So, the next thing I'm going to go over is constructing your design. And actually, can I go back to the slide with the steps real quick? Yeah, definitely. You're lucky in that we already went over a lot of this stuff before I even talked about the engineering design process, but a lot of the time engineers would just be like, well, there's something missing that we can build a program maybe to fix that. So yours is a little bit more cut and dry than a lot of engineers would have. But anyways, there's 4 different big parts to building your ROV, and the first of which you will be doing or have done in your first lab, is designing the structural system or the frame of your design. So the picture here is the default design that Perch sort of provides for you. Remember that you can always change it if you'd like, depending on any challenges that I might think up. But basically, it's just the frame of your design. Again, it's going to be 1/2-inch PVC piping, and again, it's got to hold your motors, floats, netting, weights, and whatever else that you may choose to put on your design, maybe a camera, whatever it may be. That's the first part of your construction. The second is going to be our mechanical system, which includes your motors to steer and raise your ROV from the water, and also submerge it. And again, all the motors will be sealed in wax so that they are waterproof. Motors may not work if they get waterlogged, so we're going to be using hot wax to do that. It's fun, trust me. And finally, our electrical system, which is just the controller of our design, and our testing, which is making sure it works as designed. Like I said, I didn't realize that we were doing our own individual robots, so what would happen is you would have a team do individually all of this stuff, or change roles as the other ones become irrelevant. But so you're going to be doing all this on your own. So that corresponds with our career things here. You got structural engineering, mechanical engineering, electrical engineering, and quality assurance engineering. All right. So any questions on the overall scope of what we're doing? Anything at all? I'm seeing a nope. Alright, finished a little bit earlier than I expected, but I have more for us to do, fortunately. So next class we're going to be talking about submarines and sort of how they work, which includes a lot about buoyancy. Today, given the amount of time we've got left, I'm just going to go over sort of a very, very basic history of submarines and their uses. Obviously, the submarines and ROVs are a little bit different, but they do have the same fundamental engineering things to them, specifically when it comes to buoyancy. All right. So, let's start talking about submarines, the mechanical monsters of the deep, and their history. I bet y'all didn't know that back in 1580, the first idea of how a submarine could work was created by this Englishman named William Bourne. I don't know anything about him, but he's basically the father of submarines. After that, it took 43 years to build our first working submarine. It was powered by 12 people that were used as oarsmen, which means that they propelled the ship. So it's not mechanical or anything, it's literally just manpower. And it was first tested in the River Thames. Anybody know where that is? Yep, London, England. Y'all got it. I'm sure it was a little bit easier to stay underwater back then before it got all polluted, but anyways. After that, it took about 150 years to build a straight-up submarine as we know it today. 1776, back in the infancy of America. This submarine was built by Mr. David Bushnell, and he called it the Turtle because it looked like a sea turtle floating in the water. And the first operator of it was Sergeant Ezra Lee. This is a sketch of the turtle. I do not know how this looks like a turtle at all, but use your imagination. I'm sure that he had a good reason for calling it the turtle. And then, almost 100 years later, they built the first submarine to use in the U.S. Navy, which is called the Alligator, looking very much like a submarine as we know it today. So why would it take this long between building the first one and making it an official ship of the Navy? Lack of technology. That's a testing. Another good one. I guess lack of technology is the best answer so far. Lack of ideas, not so much. People were pretty smart back then. Lack of resources, definitely some good ideas here. Specifically, I'm talking about the Industrial Revolution. That's when we really started using machines to our advantage. So really good thoughts, y'all. Maybe named it the turtle because he was in a shell. Okay, yeah, I could see that. It looks like it was human-powered as well, though. But yeah, y'all got it. That's why it took so long. We just didn't have the technology or resources or know-how or money, really, to do that. So notice that not very long after that, in 1862, in 1885, the first steam-powered submarine was launched, which had a torpedo tube. It's called the Nordenfeldt First one. You can see it being a turtle in its shell. Okay, I can see that. So first steam-built submarine that could bomb stuff, torpedo stuff. And very soon thereafter that, the British Navy had built a couple more of these guys, but a lot of people thought that these were really unfair, that were too advantageous towards the people with the submarines, and I could definitely understand that back in 1900, before planes were even a thing. And finally, 6 years later, the Germans get this technology and built the U-boats. I'm sure y'all have heard of U-boats before, be it in Call of Duty or whatever games. Very intense war submarines there. So for war, submarines were first used for World War I. They were also used in World War II, and I'll get to that in just a second. Even though they were built very recently at this point, they were very advanced. The U-boats were the first truly effective submarines. You can't go wrong with that German engineering, right? And they definitely wreaked havoc on the British and Allied warships, as well as normal shipping ships. They caused a big old stir there. And this is what the initial German U-boat looked like. So imagine hanging out on a boat back in the 19-teens and suddenly you're sinking because of this guy. Terrifying stuff. So then we get to World War II, where submarines were truly used a whole ton, and especially when Italy joined Germany, Italy being a very much bordering the Mediterranean Sea. So Germany ended up bringing 105 of these submarines into the Mediterranean, but luckily they didn't do too much. But finally, in 1941, the U-boat 570 became the first and only submarine captured by an aircraft. Think about that. Underwater caught by an aircraft, huh? But basically it was under attack, had to go to the surface and surrender. Yeah, I know, right? Weird stuff. A airplane capturing a submarine. But I'm guessing just with radar, they figured out there was a submarine underneath them. They started shooting them, and eventually the submarine was, I don't know, maybe forced to surface for whatever reason. So an escort ship did arrive and take over. This ship was taken to the Royal Navy and given a new name. And this is what, kind of a poor picture of what this new U-boat looked like. And long after it was made, there were 16 more of them. So weird stuff there, definitely. So by 1953, the next generation sub with missiles was created called the Regulus 1, which can carry 3,000-pound nuclear warhead for, 500 miles. So at this point we get nuclear subs, which we'll learn more about next class. A brilliant, brilliant, and terrifying invention in my opinion. It's crazy how they work. The next U-boat, the U-2511, left Hamburg, Germany on war control. Had to surrender, basically, and there were a ton of them getting ready to be created or had just been created. So here's that iteration of the U-boat, and where was I going with that? Well, anyways, this is weird. I should have redone this slide a little bit. I don't know why it's out of order. Anyways, at the very end of World War II, the Japanese ended up launching a huge submarine building program. Just little tiny submarines used for kamikaze, basically, except, in the water. And they called them midgets. And 84 of them are huddled in dry dock to be used probably at the very tail end of World War II. All right. So, yeah, I really need to fix this slide later. What I had mentioned earlier was about nuclear submarines being some crazy, intelligently designed submarines. The first one was designed in 1954, or was launched in 1954, called the Nautilus, over 3,000 tons, geez. It could go 18 knots on the surface or 23 knots submerged. I need to figure out how far that is in miles per hour. It could be easier for you to understand, but this is pretty darn fast. And on the very first cruise it went 1,381 miles from New London, I don't know where that is, to San Juan, Puerto Rico, all the time submerged at 15 knots. So this is crazy at the time. It didn't have to surface for air or anything for the entire 1,381 mile trip. That's roughly from the Outer Banks to Kansas. So pretty far, right? Pretty crazy that they could do that. But before the nuclear power was available, submarines were really inefficient and costly to run, hence why only the military would use them at the time. But the way nuclear submarines work, it's basically just a nuclear reactor in submarine form. So it can go very fast, very far, but obviously it's dangerous to an extent, since we are using nuclear power in the very early nuclear power days. So here's one nuclear sub, Seawolf, and there's the Nautilus I was just talking about. So I'm not going to go any farther, so we're going to save some stuff for next class. Any questions on all the crazy stuff that we learned about today? So anything about sea perch, anything about the history of submarines in general, anything like that. So seeing a couple no's. Well, if you don't have any questions, you are good to go for the day. I'll be here if you do have questions. Thanks very much for coming out today. I hope you enjoyed it, and I look forward to talking to you on Wednesday. All right, take care, y'all. So I see another question here. Can nuclear sub blow up underwater? Yes. There probably wouldn't be like a nuclear meltdown underwater because they're very well regulated by the inhabitants. But yes, they very much can blow up underwater. Alright, cool. Take care, see you Wednesday. Any more questions for me before I head out? Alright. I'm gonna head out too. Thanks a bunch.